The cosmos is a beautiful death trap. We often gaze at the stars and see only serene beauty, but the truth is far more terrifying. The universe is filled with places so hostile, they defy human imagination. Today we are going on a tour of the 25 most dangerous locations in existence. You will discover worlds where the very laws of physics twist into instruments of pure destruction. We will see points of infinite density, storms larger than planets, and voids of absolute nothingness. By the end, you will understand the sheer, awesome power of cosmic forces that could erase our world in an instant. How does a star's corpse become a weapon? What does absolute emptiness feel like? The answers lie ahead in places where survival is not just difficult, it is utterly impossible. What do you think is the most frightening force in the universe? Our journey begins at the very edge of comprehension, a place where the universe's rules break down completely. The number one most dangerous place is the singularity at the heart of a black hole. This is not a location you can visit, it is a destination you cannot escape. A singularity is a point of unimaginable density where all the mass of a collapsed star, sometimes millions of times the mass of our Sun, is crushed into a space with zero volume. Think of it as the ultimate cosmic dead end. Here, the mathematics of gravity as described by Einstein simply stop working. Concepts like space and time lose all meaning. It is a tear in the fabric of reality itself. To even approach this nightmare point, you must first cross the event horizon, the black hole's point of no return. Picture it as a one-way door. Light, information, matter, everything that passes this invisible boundary is forever lost to our universe. There is no going back, no sending a message, no hope of rescue. But the true horror begins long before you reach the central singularity. As you fall inward, the black hole's gravitational pull becomes so intense that it acts differently on different parts of your body. Your feet, being closer to the center, feel a stronger pull than your head. This difference in force, called tidal force, begins to stretch you. This process has a terrifyingly vivid name: spaghettification. You are not just pulled, you are elongated into a single, thin strand of atoms, a cosmic piece of spaghetti, before being crushed into the singularity. What happens at the singularity is the greatest mystery in physics. Our current laws cannot describe it. Some theories suggest it is a gateway to another universe, others that it is a wall of infinite energy. All we know for certain is that it represents the ultimate victory of gravity over every other force in nature. It is a one-way trip to a place where existence, as we understand it, ceases to be. So while we may marvel at black holes from a safe distance, their hearts remain the most violently destructive and unknowable locations in all of creation. Yet the singularity is not the only horror a black hole offers. Before matter vanishes forever into that point of infinite density, it must endure a different kind of hell. This brings us to our second most dangerous place, the accretion disk of a supermassive black hole. If the singularity is the bottomless pit, the accretion disk is the furious, superheated whirlpool that surrounds it. Picture a cosmic hurricane, but one made of incandescent gas, shattered planets, and the remnants of entire stars, all spiraling inward at nearly the speed of light. This is not a calm descent, it is a violent, chaotic maelstrom where the very laws of physics become instruments of torture. The material in this disk is caught in a gravitational tug of war, pulled inexorably toward the event horizon while also trying to orbit the black hole. This creates immense friction, like trillions of rocks grinding against each other in a cosmic avalanche. That friction generates staggering heat, raising temperatures to millions of degrees. At such extremes, matter does not just glow, it screams across the entire electromagnetic spectrum, blazing with X-rays and gamma rays powerful enough to sterilize entire star systems from light years away. Magnetic fields within this churning chaos become twisted and amplified, launching jets of superheated particles thousands of light years into space. To be near an accretion disk is to be inside a cosmic blender and a microwave oven simultaneously. Any object, even a star, is first stretched by tidal forces, then shredded into a stream of superheated plasma, its component atoms torn apart before they ever reach the point of no return. The accretion disk is a black hole's warning beacon, a brilliant and terrifying announcement that here, in this region of space, matter is being dismantled with ferocious energy. It is the last, spectacularly violent chapter in the life of anything unfortunate enough to wander too close. But the destructive power of a black hole is at least confined to its immediate vicinity. Our third most dangerous place is a threat that can reach across the galaxy in an instant, a cosmic sniper rifle with unimaginable firepower. This is the jet of a gamma-ray burst born from the death throes of a hypernova. When a star dozens of times more massive than our Sun finally exhausts its fuel, it does not go quietly. Its core collapses not into a quiet neutron star but directly into a black hole. In that cataclysmic moment, twin beams of concentrated energy composed of gamma radiation are blasted out from the star's poles at nearly the speed of light. These are not broad explosions, they are focused jets like the beam of the most powerful laser ever conceived. For a few seconds, a single gamma-ray burst jet can outshine every star in 100 billion galaxies combined. It is the single most luminous event in the universe since the Big Bang itself, and its danger lies in its focus and its reach. If such a jet were pointed directly at a planet like Earth, even from thousands of light years away, it would be a sterilizing event. The initial blast of gamma rays would not just hit our atmosphere, it would violently rip through it. In a flash, it would shred our protective ozone layer, the shield that blocks the sun's deadly ultraviolet radiation. With that shield gone, the surface would be bathed in lethal radiation, devastating ecosystems and triggering a global mass extinction. The gamma rays could also trigger chemical reactions in the atmosphere, creating a thick, toxic smog of nitrogen dioxide that would blot out the sun and induce a rapid ice age. The terrifying reality is that such an event is entirely random and unpredictable. It could happen in a galaxy far away tomorrow, and we would have no warning until the light and the death reached us. We are safe only through sheer cosmic luck, relying on the statistical unlikelihood that one of these universe-ending beams is currently aimed in our direction. It is a reminder that in the grand theater of the cosmos, our survival can hinge on the random orientation of a dying star halfway across the Milky Way. That kind of random annihilation from across the galaxy is terrifying, but sometimes the danger is not in a sudden flash, it is in a slow, inexorable crush. Our fourth most dangerous place is the surface of a neutron star, the corpse of a massive star that did not quite become a black hole. This is where the universe shows us the true meaning of density. Imagine taking our entire sun, a sphere over 860,000 miles across, and crushing it down until it is only the size of a major city, perhaps just 12 miles from end to end. That is a neutron star. It is a cosmic diamond forged in the heart of a supernova explosion, so dense that a single teaspoon of its material would weigh billions of tons here on Earth. You could not lift it with every crane on our planet combined. This insane density creates a gravitational field that is almost beyond comprehension. Standing on its surface, you would experience a pull millions of times stronger than the gravity you feel right now. The force would be so instantaneous and so absolute that any probe, any structure, any form of matter we know would be flattened into a film no thicker than an atom in a fraction of a second. There would be no impact crater, just a smooth, permanent addition to the star's unimaginably hard crust. But the horror does not end with gravity. Neutron stars possess magnetic fields of almost cartoonish strength. While Earth's magnetic field is strong enough to guide a compass needle, the field around a neutron star can be a quadrillion times more powerful. To be within thousands of miles of such an object would be fatal long before gravity took hold. These magnetic fields are so intense they can literally reshape matter. They stretch and distort the very atoms of anything nearby, ripping electrons away from their nuclei and creating a soup of charged particles. Any electronics on a spacecraft would be fried instantly, its circuits overloaded by colossal electromagnetic forces. Some neutron stars, known as magnetars, take this magnetic nightmare to an even greater extreme. They occasionally suffer starquakes, cracks in their unbelievably rigid surfaces, which release bursts of X-rays and gamma rays powerful enough to affect Earth's upper atmosphere from clear across the Milky Way. So while a neutron star may seem like a small, quiet ember in the darkness, it is in reality a realm of such extreme physics that it makes the core of our sun look placid and safe. It is a monument to the fact that in the universe, sometimes the most compact things hold the most violent potential. But the neutron star's magnetic field is merely a prelude. The true monarch of magnetic mayhem is the magnetar. If a typical neutron star possesses a magnetic field of unimaginable strength, a magnetar's is a force of pure cosmic vandalism. These are neutron stars born spinning incredibly fast and endowed with magnetic fields 1,000 times more powerful than their already terrifying cousins. We are talking about a field so intense it could distort the orbits of electrons within an atom from a distance of thousands of miles. To be near one is to enter a realm where physics textbooks are rewritten in real time. The magnetosphere, the region of space dominated by this magnetic field, is a perpetual storm of tortured particles. Electrons are ripped from atoms and forced to spiral along magnetic field lines at nearly the speed of light, screaming out in X-rays as they move. This creates an ambient glow of lethal radiation that would penetrate any shielding we could possibly build. But the true danger of a magnetar is not its steady state, it is its tantrums. These objects suffer from starquakes as the magnetar's insane magnetic field slowly decays over millennia. It exerts unimaginable stress on the star's iron-rich crust, a crust harder than diamond. Eventually, that crust cracks. Think of it like a tectonic plate shift, but on a sphere only 12 miles across and under pressures that make the center of the Earth seem soft. When that crust fractures, it releases more energy in 1/10 of a second than our sun will emit in 100,000 years. This energy erupts as a colossal burst of X-rays and gamma rays, a flash of pure death that can travel across the galaxy. In 2004, a magnetar 50,000 light-years away released a burst so powerful that, for a fraction of a second, it outshone the full moon despite being on the far side of our own galaxy. It compressed Earth's upper atmosphere and briefly blinded satellites. The magnetic pulse from such an event is almost beyond analogy. It is said that from a distance halfway to the moon, a magnetar's magnetic field would be strong enough to erase every credit card on Earth, not by some clever hack, but by physically scrambling the magnetic stripes with raw, overwhelming force. Within its magnetosphere, matter itself is not safe. Atoms are stretched into long, thin cylinders, their very shapes dictated by the magnetic field's will. Chemistry, the rules that govern how atoms bond to form the world around us, simply ceases to function. A magnetar does not just kill you, it dismantles the fundamental blueprint of your being before you even know it is there. It is a reminder that in the universe's arsenal, gravity has a fierce rival, and its name is magnetism. These forces of magnetism and gravity shape the cosmos on a grand scale, but sometimes the most terrifying dangers are found on worlds we once thought familiar. Our sixth most dangerous place is not a distant star or a black hole's edge. It is our own planetary neighbor, Venus. Often called Earth's twin due to its similar size and composition, Venus is a stark warning of how a world can go horrifically wrong. It is a vision of a runaway greenhouse effect taken to its ultimate, hellish conclusion. The surface of Venus is a lesson in extremes. The average temperature is a staggering 860 degrees Fahrenheit, hot enough to melt lead and incinerate any spacecraft in minutes. This heat is not merely a product of being closer to the Sun. It is trapped by an atmosphere so thick and toxic it creates a permanent, suffocating oven. Standing on the Venusian surface, you would experience an atmospheric pressure 92 times greater than what you feel on Earth. It is the equivalent of being nearly 1 kilometer deep in Earth's ocean, a crushing weight that would instantly collapse a nuclear submarine. The very air you would try to breathe is almost entirely carbon dioxide, a heavy, suffocating blanket that has turned the planet into a pressure cooker. And then there are the clouds. They are not made of water vapor, but of corrosive sulfuric acid, creating a perpetual, burning rain that evaporates long before it ever reaches the scorched ground below. This toxic atmosphere is not static. It is a violent, churning beast. It super-rotates, meaning the entire blanket of gas whips around the planet once every 4 Earth days, while the solid planet below only spins once every 243 days. This creates hurricane-force winds that scream across the entire planet, driving a global storm system of unimaginable fury. Probes that have landed on Venus did not simply stop working. They were crushed, melted, and dissolved by an environment that seems personally offended by the presence of anything solid. Venus shows us that the delicate balance that makes our own world habitable is a precious and fragile thing. It is a prime example of planetary climate pushed past the breaking point, a permanent monument to the destructive power of a trapped sun. Venus is a monument to atmospheric fury, but it is not the only world in our solar system with a permanent storm. For our 7th most dangerous place, we look outward to a swirling vortex of crimson madness that has watched the dinosaurs come and go. This is Jupiter's Great Red Spot, an anticyclonic storm so vast and so ancient it makes every hurricane in Earth's history look like a fleeting breeze. This is not merely a weather pattern, it is a planetary-scale predator, a perpetual engine of chaos that has raged for at least 350 years and possibly much longer. Its scale defies easy understanding. The Great Red Spot is large enough to swallow our entire planet whole, with room to spare. If you placed Earth inside this monstrous storm, you would lose our world completely within its swirling brick-red clouds. What fuels a tempest of such impossible endurance? The winds screaming around its edges are a key to the horror. They whip around the storm's perimeter at speeds exceeding 400 miles per hour, more than twice the force of the most powerful Category 5 hurricane ever recorded on Earth. These are not gusts, they are a permanent, supersonic river of gas carving a path through Jupiter's upper atmosphere, but the true danger lies within. The spot is not a shallow surface feature. It is a deep wound in the planet's flesh, a storm that likely extends hundreds of miles down into the gaseous abyss. As you descend through its layers, the environment becomes increasingly hellish. The beautiful, banded clouds give way to unimaginable pressures, crushing forces that would compact any spacecraft into a tiny, dense sphere. Within these deep, turbulent layers, the chemistry turns alien and violent. Complex organic molecules are churned, shattered, and recombined by the storm's immense energy, creating a toxic soup of compounds we can scarcely identify. And then there is the lightning. Deep within the Great Red Spot, lightning storms erupt that dwarf anything on our world. These are not single bolts, but continuous, continent-sized sheets of electrical discharge, flashing with power 1,000 times greater than their terrestrial cousins. They illuminate a cavern of churning ammonia and water, a hidden, violent heart beating within the storm. The Great Red Spot is a testament to a simple, terrifying truth: on a gas giant, weather is not an event. It is a permanent geological force. It is a self-sustaining maelstrom that eats smaller storms, pulses in size, and changes color, but never, ever dies. It is a perpetual motion machine of destruction, a landmark of pure atmospheric violence that has been the largest and most dangerous storm in our solar system for centuries. It asks a haunting question: what must it be like to fall into a whirlpool that is wider than your entire world and has been spinning since before your civilization began? Jupiter's relentless pull does more than fuel eternal storms. It also tortures a world right next door. Our eighth most dangerous place is the volcanic plains of Io, a moon that looks like a cosmic pizza left in the oven too long. This is the single most volcanically active body in our entire solar system, a world where the very ground is alive with fury. The driving force behind this hellscape is a gravitational tug of war. Io is caught in an orbital dance between the massive gravity of Jupiter and the rhythmic pulls of its sister moons, Europa and Ganymede. This constant stretching squeeze, called tidal heating, flexes Io's interior like a ball of clay being kneaded by a giant. That friction generates immense heat, melting rock from the inside out and powering a global network of volcanoes that never sleep. The surface of Io is a canvas of ongoing destruction. Vast plains are coated in fresh layers of sulfur and silicate lava, painted in garish yellows, oranges, and reds from various sulfur compounds. Here you can find lakes of molten sulfur simmering in broad, dark depressions. But the true spectacle is in the eruptions. Plumes from Io's most powerful volcanoes blast hundreds of miles into the thin sky, forming umbrella-shaped columns of gas and ash that fall back to coat entire regions in poisonous frost. These are not like terrestrial volcanoes. They are continuous, planet-wide vents for the moon's internal torment. Lava flows on Io are colossal, some longer than the entire Nile River, and so hot they glow with an incandescent rage visible from space. Yet the geological violence is only half the danger. Io orbits deep within Jupiter's ferocious radiation belts, a zone of charged particles trapped by the planet's magnetic field. The surface is bombarded by this radiation incessantly. An astronaut standing on Io, even in a heavily shielded suit, would receive a lethal dose in mere hours. This creates a uniquely double-layered hell. You are standing on a crust that could crack open beneath your feet at any moment, spewing superheated lava, while simultaneously being cooked by an invisible hail of atomic particles from above. The very atmosphere, thin as it is composed largely of sulfur dioxide expelled from the volcanoes, making each toxic breath a cocktail of poison. Io is a world with no respite, no quiet corner. It is a vivid demonstration of how orbital mechanics can turn a world into a pressure cooker, and a warning that sometimes the most terrifying places are those caught in an inescapable gravitational embrace. While Io is a world torn apart by gravity's constant pull, Saturn presents a different kind of orbital danger, one written in ice and silence. The beautiful rings of Saturn are not just a decoration, they are a graveyard and a lethal obstacle course. Their existence is governed by a precise and terrifying boundary known as the Roche limit. This is the distance from a planet within which the tidal forces pulling an object apart become stronger than the gravity holding it together. Think of it as a planet's personal shredding zone. If a moon, an asteroid, or even a spacecraft ventures inside this invisible line, it will be systematically dismantled. Saturn's magnificent rings are believed to be the glittering remains of a moon or a large comet that once drifted too close, crossing that fatal threshold. The planet's gravity did not simply capture it, it performed a slow, meticulous dissection. The object was stretched and pulled until every mountain, every boulder, every speck of ice was separated from its neighbors, creating the vast, flat disk of debris we see today. This is the permanent aftermath of a celestial execution, but the rings are not a static memorial, they are an active hazard. They are composed of countless fragments, from house-sized chunks of water ice down to particles finer than dust. All of them are in orbit, whipping around Saturn at tremendous speeds. To attempt navigation through this region would be an exercise in suicidal precision. A collision with even a pebble, when both you and it are moving at tens of thousands of miles per hour, would release the energy of a large bomb, instantly vaporizing any spacecraft. The resulting shockwave would likely trigger a catastrophic chain reaction, as shattered hull fragments collide with more ice, creating a cascading cloud of high-velocity shrapnel. It would be less like flying through an asteroid field and more like blasting through a cosmic shotgun blast. The rings are a breathtaking vista from afar, but up close they represent a zone of pure orbital chaos, where the laws of physics have arranged beautiful, glittering destruction on a scale that defies human engineering. They serve as a stark reminder that in space, beauty and annihilation are often two sides of the same coin. That relentless cosmic bombardment from Jupiter is a distant threat, but our own star holds a more immediate and personal danger. The Sun is not a placid ball of light, it is a churning nuclear furnace with a violently unstable temper. The true danger zone is not its blazing surface, but the mysterious, superheated halo that surrounds it, the corona. This is the Sun's outer atmosphere, a wispy, ethereal veil of plasma that extends millions of miles into space. Its very existence is a profound mystery, because while the Sun's visible surface simmers at around 10,000 degrees, the corona soars to temperatures in the millions. It is as if you walked away from a campfire and suddenly the air a foot away became 1,000 times hotter than the flames themselves. This superheated plasma is not static. It is constantly streaming away from the Sun as the solar wind, a ceaseless, invisible gale of charged particles that bathes the entire solar system. But when the Sun's tangled magnetic field lines suddenly snap and reconnect, it unleashes true fury. These are solar flares, catastrophic explosions on the solar surface. In mere minutes, a single flare can release energy equivalent to millions of 100 megaton nuclear bombs detonating simultaneously. The flash of X-rays and extreme ultraviolet radiation races toward Earth at the speed of light, reaching us in just over 8 minutes. This radiation surge can ionize our upper atmosphere, disrupting radio communications and GPS signals across entire hemispheres, and bathing any astronaut outside their spacecraft shielding in a dangerous dose of radiation. Yet the flare is often just the warning shot. The more insidious threat follows behind, traveling much slower. This is the coronal mass ejection, a CME. Imagine the Sun having a volcanic eruption, but instead of lava, it blasts out 1 billion tons of its own magnetized atmosphere, a cloud of plasma as wide as the Sun itself directly into space. If this colossal bubble is aimed at Earth, it takes 1 to 3 days to arrive. When it finally hits our planet's magnetic field, the results are spectacular and potentially devastating. The impact compresses our magnetic shield on the day side and stretches it into a long tail on the night side, funneling charged particles toward the poles to create intense auroras. But the real danger is in the induction. That moving magnetic field from the Sun can induce enormous electrical currents in anything long and conductive on Earth, like power lines, oil pipelines, and undersea communication cables. In March of 1989, a powerful CME struck Earth, and within 90 seconds, the entire power grid in Quebec, Canada, collapsed, leaving millions without power for 9 hours in the dead of winter. A similar event today, in our far more electronically dependent world, could cause trillions of dollars in damage, triggering widespread blackouts that could last for months. Our satellites, the backbone of modern navigation, communication, and finance, are on the front lines. A direct hit from a CME can fry their delicate electronics, turning multi-million-dollar assets into useless space junk in an instant. We live in the atmosphere of a star, and its weather is a constant, invisible siege. The rhythmic fury of a magnetar is matched only by the relentless, ticking precision of another neutron star nightmare. A pulsar is a cosmic metronome of death, a rapidly spinning stellar corpse that sweeps the darkness with focused beams of pure radiation. Born in the supernova explosion of a massive star, a pulsar is what remains when a neutron star is set spinning at a dizzying rate, sometimes hundreds of times per second. Its powerful magnetic field, while not quite as intense as a magnetar's, channels charged particles toward its magnetic poles, where they are accelerated to near light speed and blasted out into space as narrow, concentrated beams of radio waves, X-rays, and gamma rays. These beams do not shine in all directions. They shoot out from the poles like the beams of the most powerful lighthouse ever built. And because the star's magnetic axis is tilted relative to its spin axis, these beams sweep through space in a regular, repeating pattern. From our distant vantage point, this creates the iconic pulse, a flash of radiation that appears with clockwork precision each time the beam sweeps across our line of sight. But up close, that regularity is a terrifying trap. The environment surrounding a pulsar is a maelstrom of lethal energy. The space near it is filled with a storm of high-energy particles, a permanent haze of X-rays and gamma rays that would penetrate any known shielding. Yet the true, surgical danger is in the beams themselves. Each sweep is like the blade of a cosmic scythe, carving a path of annihilation through the void. To be caught directly in one of these focused beams, even for a fraction of a second, would be catastrophic. The energy delivered would be equivalent to absorbing the total output of our sun for an entire year, all compressed into a single blinding instant. It would not just destroy a spacecraft, it would vaporize it, breaking its atoms down into a cloud of dissociated particles. Navigating near a pulsar would be an exercise in suicidal timing. You would need to predict the exact millisecond the beam would pass your location and maneuver with impossible accuracy to stay within the narrow, safe windows between each lethal sweep. One timing error, one calculation mistake by a thousandth of a second, and you are erased from existence by a rhythmic, indifferent flash. It is a realm where chaos has been refined into a perfect, predictable rhythm of death. A reminder that in the universe, even order can be a weapon. The pulsar's rhythmic death ray is a beacon of focused fury, but there are places in the cosmos where all such violence fades into a profound and chilling silence. Between the great islands of stars we call galaxies lies the true void, a vacuum so perfect it defies human instinct. This is the intergalactic medium, and its danger is not in what it does, but in what it does not do. After the crushing gravity and searing radiation of other cosmic locales, the emptiness here is a different kind of terror. It is a near-perfect vacuum, with perhaps just a single atom floating in a space the size of a typical bedroom. The temperature hovers just a few degrees above absolute zero, the point where all molecular motion stops. There is no air, no warmth, no medium to carry sound or sensation. It is the ultimate sensory deprivation chamber, scaled to the size of the universe. For a traveler adrift here, the physical peril is immediate and total. Exposure to this vacuum would cause the fluids on your eyes and tongue to boil away at body temperature, not from heat but from the lack of pressure. Your body would swell and your lungs would rupture in seconds. But death would be a swift mercy compared to the psychological eternity that follows. You would be utterly alone, separated from the nearest star by millions of light years of nothing. The galaxies themselves would appear as faint, fuzzy smudges of light, beautiful but impossibly distant. There would be no day, no night, only an unbroken, starless black in every direction. The silence would be absolute, a weight pressing in from all sides. This isolation is a form of torture the human mind is not equipped to handle. Yet, even in this perfect emptiness, a low-grade threat persists. The void is not completely empty of energy. It is constantly threaded by cosmic rays, high-energy atomic nuclei traveling at nearly the speed of light. Within galaxies, magnetic fields can deflect or slow these particles. But here, in the intergalactic void, there is nothing to stop them. They fly unimpeded across the cosmic gulf, silent, invisible bullets that would pierce a spacecraft's hull and the bodies of any occupants within, damaging cells and shredding DNA over time. To be here is to be simultaneously frozen, suffocated, irradiated, and driven mad by the sheer, overwhelming absence of everything. It is a reminder that in the universe, violence is not the only danger. Sometimes the most terrifying place is nowhere at all. But the most violent engines in the universe are not content to merely destroy what falls into them. They seek to dominate the space around them for millions of light years. At the heart of an active galaxy lies a true apocalypse in progress, an active galactic nucleus. This is a supermassive black hole's feeding frenzy scaled up to a galactic catastrophe. While a typical black hole might snack on the occasional star, the monster at the center of an active galaxy is a glutton of cosmic proportions, consuming vast quantities of gas, dust, and entire solar systems that spiral into its accretion disk. This process does not just create a local hazard, it ignites the entire core of the galaxy into a furnace of unimaginable power. The infalling matter, heated to millions of degrees, blazes with a light so intense it can outshine every single star in the galaxy combined. When such a core is pointed directly at us, we call it a quasar, a beacon of raw energy visible across the universe. The light from a quasar is not gentle starlight. It is a screaming torrent of radiation across the entire spectrum, from radio waves to lethal gamma rays, pouring out from a region not much larger than our solar system. This radiant fury is so overwhelming that it can literally blow a galaxy apart from the inside out. The energy pouring from the active nucleus heats the surrounding gas to such extremes that it cannot cool down and collapse to form new stars. It stifles the very birth of suns, effectively sterilizing vast regions of its host galaxy and condemning it to a slow, hot death. Yet the true signature of an active galactic nucleus is even more dramatic: the relativistic jets. These are twin beams of plasma, charged particles accelerated to over 99% the speed of light by the black hole's insane magnetic fields. They erupt from the poles of the accretion disk and blast their way clear through the galaxy, extending for hundreds of thousands of light years into intergalactic space. To be anywhere near the path of one of these jets is to experience a cosmic blowtorch of biblical scale. The particles within them carry so much energy that they glow with a brilliant synchrotron radiation, often visible in radio wavelengths. Where these jets plow into the tenuous gas between galaxies, they create colossal, glowing lobes of energy that can be larger than the galaxy itself. These jets are the black hole's way of asserting dominance, regulating the growth of its entire galactic home and influencing the space around it for millions of years. An active galactic nucleus is not a place, it is an event, a phase of galactic violence where the central black hole temporarily becomes the brightest, most dangerous object for billions of light years around, a true monarch of cosmic ruin. A galactic empire of light and violence seems absolute, but some dangers defy even that scale by rejecting the sun entirely. Adrift in the infinite dark between stars are orphaned worlds, planets torn from their solar systems by gravitational chaos and sent on eternal journeys through the void. The surface of a rogue planet is a monument to absolute desolation. Without a star to orbit, it knows no day, no season, no year. It is a sphere of perpetual midnight where the only illumination comes from the faint, frozen glitter of distant galaxies, a glow too weak to even cast a shadow. Any warmth from its formation has long since bled away into space, leaving surface temperatures that plunge toward absolute zero, colder than even the void of intergalactic space. An atmosphere, if it ever had one, would have long ago collapsed, freezing solid into a blanket of ice or settling as a global ocean of liquid helium on the surface, a frigid, sluggish soup where chemistry grinds to a halt. Here, the very concept of weather is dead. There is no wind, no storm, only a profound and motionless freeze. The silence would be deeper than anywhere else, broken by no seismic rumble, for the core is likely geologically dead, its internal fires extinguished eons ago. The only heat might come from the faint, lingering decay of radioactive elements in its heart, a dying ember utterly incapable of reaching the surface. To stand on such a world is to experience the ultimate abandonment. You are on a rock falling forever through a black ocean, where the horizon in every direction is nothing but an unbroken curve of darkness against a starless sky. There is no energy to harvest, no fuel to burn, no hope of photosynthesis or external warmth. It is a tomb with a view of the entire universe, a perfect prison of cold and dark where time itself seems to have stopped. This is a danger defined not by fury, but by the utter, irreversible withdrawal of all that makes a world alive. Even Jupiter's magnificent storms are merely surface decorations compared to the invisible fortress that surrounds it. The true danger zone of the gas giant is not its clouds, but its magnetosphere, a vast, invisible bubble of magnetic influence that is the largest structure in our solar system. If you could see it from Earth, it would appear larger than the full moon in our sky, a colossal shield of pure force. Trapped within this magnetic prison are the most ferocious radiation belts in our entire cosmic neighborhood, often called Van Allen belts on a terrifying dose of steroids. These are not gentle rings of energy, they are tornadoes of atomic violence. Jupiter's powerful magnetic field acts like a colossal particle accelerator, snatching electrons and protons from the solar wind and from its volcanic moon Io, then whipping them to nearly the speed of light. These charged particles become trapped, spiraling along magnetic field lines in a relentless, high-energy dance between the planet's poles. The result is a permanent, searing haze of radiation that envelops the entire Jovian system. For any machine or living thing, this zone is instant death. A spacecraft's delicate electronics, its computer brains and sensor eyes would be bombarded by this particle hail. The high-energy electrons would penetrate shielding, bury themselves in microchips, and cause what engineers call bit flips, turning ones into zeros and corrupting data at random. Over time, the cumulative dose would physically degrade the silicon itself, turning precise circuits into useless, radioactive confetti. For a human, the outcome is swifter and more gruesome. An astronaut inside even a heavily shielded capsule near Jupiter would receive a lethal dose of radiation in mere minutes. The invisible particles would slice through cells, shattering DNA strands and causing catastrophic, irreparable damage to the body's vital systems. There is no suit, no medication, and no quick escape from this kind of atomic barrage. The data from the Galileo probe, which orbited Jupiter in the 1990s, paints a stark picture of this hellish environment. Its radiation-hardened systems were pushed to their absolute limits. The probe's camera suffered constant noise and degradation from particle strikes, like static on an old television broadcast from a war zone. Other instruments failed prematurely, their circuits cooked from the inside out by the relentless assault. Galileo's mission designers knew the probe was marching to its death from the moment it arrived, its lifespan measured not in years, but in how long its shields could hold out against the storm. This radiation fury makes any mission to Jupiter, even a simple flyby, one of the greatest engineering challenges in space exploration. Engineers must design spacecraft with vault-like radiation shielding, often using thick layers of titanium and specialized plastics, and place sensitive electronics deep within a protective vault. They must plan orbits that minimize time in the most intense zones, a delicate dance with an invisible dragon. To venture into Jupiter's realm is to knowingly send your creation into the heart of a perpetual atomic fire, a reminder that some of the universe's most potent dangers are those you can never see. Mercury offers a different kind of solar system hell, a world of punishing extremes defined by absence. It is the solar system's speedster, orbiting the Sun in a blistering 88-day year, yet it possesses almost no atmosphere to speak of. This lack of a protective blanket is the source of its unique torment. Without an atmosphere to trap heat or distribute warmth, the surface exists in a state of violent thermal shock. In the direct glare of the sun, ground temperatures can soar to a searing 430 degrees Celsius, hot enough to melt lead and zinc. But step into the shadow of a crater wall or wait for the long Mercurian night to fall, and the very same rock plummets to a soul-crushing negative 180 degrees Celsius. This is not a gentle cooling off, it is a plunge of over 600 degrees. Imagine the stress this places on any solid material. The rocks themselves expand in the brutal sunlight, then contract violently in the deep freeze of night. Over millions of years, this relentless thermal cycling acts like a hammer, gradually fracturing the surface into a fine, dusty regolith. For any human structure or spacecraft, the effect would be catastrophic and swift. Metal joints would warp and crack, seals would fail, and glass would shatter from the constant grinding stress. You could not build a base that could withstand baking in an oven by day and being dunked in liquid nitrogen by night, over and over again. Compounding this thermal nightmare is Mercury's proximity to the Sun itself. It bathes in a flood of solar radiation nearly 7 times more intense than what we experience on Earth. The surface is not just hot and cold, it is also being constantly sandblasted by the solar wind and ultraviolet rays, baking any complex chemistry out of existence. The result is a barren, cratered landscape that is simultaneously a scorching desert, a deep freeze wasteland, and a radioactive griddle. It is a world where the environment itself is engaged in a perpetual, destructive war between absolute heat and absolute cold, with no middle ground and no mercy for anything caught in between. The violence of a formed solar system pales in comparison to its chaotic birth. Before planets found stable orbits, they existed in a swirling, primordial storm known as a protoplanetary disk. Picture a vast, flat whirlpool of gas and dust, light years across, spinning around a newborn and temperamental star. This is not a peaceful cosmic cradle. It is a brutal construction zone where creation is forged through relentless, shattering collisions. Within this thick, opaque disk, microscopic particles of ice and rock begin to stick together, slowly growing into mountain-sized chunks called planetesimals. These are the building blocks of worlds, but their assembly is a violent, chaotic process. The disk is filled with trillions of these objects, all on different, crossing paths. Collisions are not occasional accidents, they are constant events. A hailstorm of debris rages, with impacts occurring at thousands of miles per hour, shattering nascent worlds as quickly as they form. To be inside this disk would be to navigate an endless, high-speed demolition derby where every other object is a potential bullet. The young star at the center adds its own lethal elements to the mix. It is a volatile toddler prone to furious tantrums of ultraviolet radiation and powerful stellar flares that blast the surrounding disk. This intense radiation ionizes the gas, stripping electrons from atoms and creating a searing environment that would break apart complex molecules necessary for life. Powerful magnetic fields generated by the star's rapid rotation and the churning disk itself twist through the chaos. These fields can accelerate particles to high speeds and channel material in unpredictable ways, adding another layer of violent unpredictability to the nursery. This is a place where gravity's gentle pull is drowned out by the cacophony of constant impacts and searing energy. It is a system where survival is measured in millennia, as only the largest, most resilient clumps of matter can withstand the bombardment long enough to sweep up debris and clear a path, eventually becoming the planets we know today. In this violent nursery, every world you see is a testament to an ancient war it somehow won. The aftermath of a stellar death is not a quiet graveyard but a continuing explosion. A supernova remnant is a cosmic blast wave, a billion-mile-per-hour tsunami of fire and shattered star stuff. This is not a static cloud, it is a titanic shock front, the outermost edge of the star's final scream, still plowing through interstellar space. The bubble it creates is a cauldron of pure chaos filled with gas heated to millions of degrees. This material is not just hot, it is screaming. Atoms are ripped apart, their electrons stripped away in the violence, creating a searing plasma that glows fiercely across the entire spectrum. From the core, a torrent of X-rays and gamma rays floods outward, a lethal background hum that would penetrate any conceivable shield. Yet the visible light is often deceptively beautiful, with delicate filaments and veils of color created by different elements: oxygen glowing green, hydrogen shining red, and sulfur in deep gold. This beauty is the ghost of the catastrophe, a radiant echo of the destruction. To be inside this expanding bubble, however, would be to experience that destruction firsthand. You would be immersed in a hurricane of atomic shrapnel. The shockwave itself, the leading edge of the remnant, moves at hypersonic speeds, compressing and heating any gas it encounters. Ahead of it, particles are swept up and accelerated to incredible velocities, some reaching over 99% the speed of light. These become cosmic rays, the universe's natural particle accelerators, firing invisible, high-energy bullets in all directions. The environment is a crossfire of radiation and matter. Even if you could somehow withstand the intense heat, you would be bombarded from within. Those cosmic rays would pierce through any material, smashing into the nuclei of your own atoms, triggering cascades of secondary particles that would ravage living tissue and scramble electronics. It would be like floating inside the heart of a thermonuclear explosion that lasts for thousands of years, surrounded by a shimmering, deadly aurora that signals your certain doom. The remnant is a factory for the very elements that make up our world: the carbon in our bones, the iron in our blood, forged in a furnace so violent we can only witness it from a safe, breathtaking distance. Our own sun's singular pull is a simple, steady force compared to the cosmic tug-of-war of a close binary star system. Here, two stars are locked in a tight, whirling dance around their common center of gravity, and the space around them is a gravitational minefield. Unlike the stable, predictable orbit of a planet around a single star, this is a landscape of shifting, competing forces. The gravity wells of the two stars overlap and interfere, creating zones of chaotic instability where a simple circular path is impossible. For any object caught between them, a planet, an asteroid, or a spacecraft navigating this space, is like trying to walk a tightrope during an earthquake. There are only a few very special orbits called Lagrangian points that offer any stability, and they are precise, fragile islands in a raging sea of gravitational chaos. The classic science fiction image of a double sunset, like on Tatooine, paints a serene picture, but the reality is far more violent. A planet attempting to orbit both stars in a wide, stable path is constantly being tugged first by one star, then the other. This creates a rhythmic stretching force, a relentless tidal pull that can heat the planet's interior to a molten state, triggering global volcanism far more intense than on Io. Worse, the subtle gravitational nudges from the two stars can gradually perturb a planet's orbit over millions of years, pushing it onto a path that leads to catastrophe. The planet could be flung inward, spiraling to be consumed by one of the stars in a fiery demise. Alternatively, it could be hurled outward at tremendous speed, ejected from the system entirely to become a frozen rogue planet, condemned to an eternal journey through the interstellar dark. For a spacecraft, the danger is immediate and calculable. A minor course correction in the wrong part of this complex gravitational field could be amplified exponentially. Instead of a gentle slingshot maneuver, the vessel might be sent careening into one of the stars or whipped off into the void on an escape trajectory from which there is no return. The space between the stars is not empty either. It is often filled with streams of gas pulled from one star to the other, creating a superheated, turbulent medium that would scour any hull. A binary system is a beautiful demonstration of celestial mechanics, but it is also a reminder that where gravity's dance becomes a duel, stability is the first casualty. The gravitational chaos of a binary system is a battle of titans, but there is another kind of alien world where the danger is a slow, chemical freeze. Saturn's largest moon, Titan, hides a landscape that is hauntingly familiar and utterly hostile. Here, rivers carve channels through icy highlands, feeding into vast, dark lakes that dot the poles. Yet these are not bodies of water. In the punishing cold of -179 degrees Celsius, the liquid flowing across Titan's surface is methane and ethane, simple hydrocarbons that are gases on our warm Earth. This is a world where the very bedrock is water ice, hard as granite, and where a dropped wrench would not splash but shatter like glass. The cold is so profound it alters the fundamental properties of materials. Plastics would become brittle and fracture, metals would contract and grow dangerously weak, and any electronic system would fail almost instantly as its components freeze solid. To stand on Titan is to inhabit a twisted mirror of our own planet, where the chemistry of life is replaced by the chemistry of deep freeze. The sky above is a perpetual orange haze, a thick blanket of nitrogen and methane that obscures the sun and presses down with a surface pressure 50% greater than Earth. This atmosphere is not just an obstacle to vision, it is a reservoir for bizarre weather. Methane rains from the sky not in gentle showers, but in slow, heavy droplets that gather into flowing rivers and standing seas. The potential for strange chemistry within these lakes is immense. Mixed with ethane and dissolved nitrogen from the atmosphere, they could form slushy, unstable mixtures or even exotic clathrates, icy cages that trap gas molecules. Some scientists speculate that beneath the icy crust, a global ocean of liquid water and ammonia might exist, kept from freezing by tidal heating from Saturn. If that subsurface ocean finds a way to erupt, it would not be with molten rock, but with a freezing slurry of water, ammonia, and methane acryvolcano that would spread a glacier of exotic ice across the already frozen landscape. For any Earth-born machinery or life, Titan is a multifaceted death trap. The cold alone is a swift killer, but the hydrocarbons themselves are insidious. Methane is an asphyxiant in this dense atmosphere, and liquid methane would act as a potent solvent, dissolving and weakening many materials we rely on. A human without protection would not only freeze and suffocate in seconds, but their very cells would be pickled and broken down by the alien chemistry. Titan is a monument to the fact that a world can have all the complex geology and meteorology of Earth, yet be rendered absolutely lethal by a simple, profound shift in temperature. It proves that oceans and rivers are not always signs of refuge. Sometimes they are the feature of a beautifully crafted prison of ice. Tiger stripes scar the gleaming ice of Saturn's small moon Enceladus. From these 4 parallel fissures near its south pole, magnificent plumes of water ice and vapor erupt hundreds of miles into space, creating a faint, ethereal ring around Saturn itself. This is not a dead, frozen ball, but a world with a beating heart, a global, salty ocean hidden beneath an icy crust, kept liquid by the gravitational kneading of Saturn's immense pull. The plumes are this hidden ocean's breath, a continuous geyser venting its secrets directly into the void. For a spacecraft, this presents an irresistible scientific opportunity and a lethal navigational hazard. Flying through the plume to sample its contents seems like a straightforward mission, but the reality is a high-stakes game. The plume is not a gentle mist, it is a blizzard. It is filled with tiny ice particles, some fine as dust, others as large as sand grains, all being blasted outward at speeds exceeding 800 miles per hour. At such velocities, even a microscopic grain of ice can act like a bullet, pitting viewports, shredding thermal blankets, and damaging sensitive external instruments. A spacecraft must carefully pick its path, threading the needle between collecting precious samples and being sandblasted into oblivion. The source of these plumes, the tiger stripe fractures themselves, add another layer of danger. These are not static cracks, but active, shifting wounds in the Moon's surface. They radiate significant heat, far warmer than the surrounding ice, indicating they are the direct conduits to the subsurface ocean. Their geometry is complex and unpredictable, with walls that may be actively shifting, collapsing, or resealing. Attempting to land near one would be like building a research station on an active glacier calving into the sea. The ground itself is unstable, capable of sudden shifts or new eruptions without warning. The very act of sampling could trigger an unforeseen reaction, perhaps a larger, more violent jet of material. Enceladus teaches us that in the cosmos, beauty is often the banner of a hidden and volatile power, a reminder that sometimes the most alluring destinations require navigating a storm of frozen knives. Its atmosphere would be a canvas of perpetual, hyperviolent weather. Brown dwarfs are the universe's failed stars, objects too massive to be planets, but not quite massive enough to ignite the sustained nuclear fusion that defines a true star. They occupy a strange purgatory, glowing not with starlight, but with the dull, residual heat of their gravitational birth. This fading warmth creates an environment of oppressive gloom and bizarre chemistry. The gravity on such a world is immense, many times stronger than Jupiter's, crushing its thick, gaseous atmosphere into a dense, high-pressure soup. Within this soupy gloom, the weather is not driven by a sun, but by the internal heat slowly leaking into the cold of space. The result is a global, churning turbulence that makes Jupiter's great red spot seem like a gentle breeze. Convection cells the size of continents rise and fall, driving winds that scream at thousands of miles per hour. And here, the clouds are not made of water or ammonia. In the searing heat and crushing pressure, they condense from vaporized rock and metal. Picture clouds of molten iron, droplets of liquid silicate essentially, raining molten sand and liquid iron. These droplets would not fall like gentle rain. They would plummet in torrential, scalding downpours, only to vaporize again in the deeper, hotter layers, creating a perpetual, hellish cycle of condensation and evaporation. The sky would be a stratified nightmare with layers of different exotic clouds, perhaps sodium sulfide or corundum, the mineral that forms rubies and sapphires, all swirling in the perpetual tempest. The light on the surface, if you could call it that, would be a dim, blood-red or dull magenta glow, barely enough to see by, emanating from the hot gases below. It is a world of eternal twilight, crushed by gravity, scoured by metallic storms, and illuminated only by its own dying ember formation. A brown dwarf is a dark monument to almost stardom, a realm where the weather itself is forged from the bones of planets that never were. Deep within the crowded stellar core of our galaxy lies a different order of chaos. The galactic center, the region surrounding the supermassive black hole Sagittarius, a star, is the metropolis of the Milky Way, and it is a metropolitan center of pure, radiant violence. Here, space is not empty. It is packed with stars, millions of them, crammed into a volume that near our solar system would be virtually vacant. The stellar density is so extreme that the average distance between stars is a mere fraction of a light year, compared to the 4 light years separating our sun from its nearest neighbor. In this urban jungle of suns, the night sky would be a perpetual, blinding day. Thousands of stars would shine with the brilliance of Venus or even the full moon, casting multiple, shifting shadows on any barren world. This light is not gentle starlight, however. It is a constant, searing bath of ultraviolet and X-ray radiation from countless massive, young and dying stars. The environment is soaked in ionizing energy, a background hum of destruction that would strip away atmospheres and break down complex molecules with ease. Adding to this radiant fury are the remnants of frequent supernova, their expanding shockwaves crisscrossing the region, creating overlapping bubbles of million-degree gas and accelerating particles to relativistic speeds. The supermassive black hole itself, Sagittarius, a star, may be relatively quiet now, but its presence dominates the dynamics of everything. Its immense gravity orchestrates a frenzied dance. Stars whip around it at breathtaking velocities, some completing an orbit in just a few Earth years. This creates a zone of extreme gravitational turbulence. The subtle tugs from so many massive objects, combined with the black hole's central pull, make stable, circular orbits nearly impossible. Stars are constantly being nudged, their paths perturbed in unpredictable ways. This gravitational pinball can send a star hurtling inward on a death spiral toward the black hole's accretion disk, or it can fling another outward on a hyperbolic escape trajectory. Worse, it can set two stars on a direct collision course. In the galactic suburbs where we live, stellar collisions are unthinkably rare. Here, in the dense core, they are a genuine statistical probability. A close encounter or a direct impact between two stars would release an apocalyptic flash of energy, briefly outshining the rest of the galaxy combined and sterilizing any planetary system within light years. To exist in the galactic center is to live in a radiant gravitational shooting gallery where the sky is both breathtakingly beautiful and terminally hostile. That radiant, crowded core is a glimpse of a galaxy in turmoil, but it is only a faint echo of a true cosmic monarch in its prime. A quasar is an active galactic nucleus turned up to its maximum volume, a beacon of pure annihilation so bright it can outshine 1,000 Milky Ways combined. All that staggering power originates from a single, gluttonous supermassive black hole, but the black hole itself is not the source of the light. The light comes from the emission zone, the furious whirlpool of matter just outside the event horizon. As gas, dust, and entire stars spiral into this cosmic drain, they do not go quietly. They are torn apart by tidal forces, superheated by friction, and accelerated to relativistic speeds, creating a disk of plasma that shines with a light more terrible than any sun. This is not a gentle glow. It is a screaming torrent of energy across every wavelength imaginable, from long, rolling radio waves to the shortest, most piercing gamma rays. If you could see the full spectrum, the quasar would not be a point of light, but a blazing, multi-colored siren of pure force. The emission zone is where physics is pushed past any reasonable limit. The radiation pouring out is so intense that it creates an environment unlike any other. Any solid object, any known material, would not simply melt under this assault. It would be instantly vaporized, its atoms blasted apart into a diffuse cloud of subatomic particles before it even realized it was falling. The radiation pressure alone, the physical push exerted by that torrent of photons, would be like standing in the exhaust plume of 1 billion rockets, a force that could halt the collapse of gas clouds and literally blow a galaxy clean of star-forming material. At these energies, light is no longer just illumination, it is a particle weapon of cosmic scale. The high-energy photons, the X-rays and gamma rays, carry enough punch to knock electrons clean off their atoms from distances of thousands of light years, a process called ionization. This creates a vast bubble of seared, electrically charged plasma around the quasar, a sterile zone where normal chemistry cannot occur. To witness such a thing up close is an impossible thought experiment. You would be erased by the light before your eyes could process the image, dissolved into your component particles by the very signal that carried the news of your destruction. A quasar is the universe showing off its ultimate power source, a statement written in radiation so fierce it can be read from the edge of the observable cosmos. This terrifying tour across the cosmos reveals a universe of breathtaking violence. From the crushing singularities of black holes to the silent, frozen tombs of rogue planets, we have witnessed locations where the laws of physics become instruments of pure destruction. Yet there is a profound duality to this chaos. These same cataclysmic forces are the universe's essential engines of creation and change. The supernova that sterilizes a star system also forges the heavy elements that form planets and life. The quasar that blows a galaxy apart also seeds future stars with enriched material. The chaotic protoplanetary disk is the violent nursery from which stable worlds are born. Our very existence is a product of these cosmic dangers, a testament to the fragile balance between creation and annihilation. We are the children of stellar explosions and gravitational chaos, living on a pale blue dot suspended in a web of unimaginable ferocity. And yet, we look up, we send probes into the radiation belts of Jupiter and plot courses to distant, frozen moons. Our drive to explore, to understand these terrifying frontiers, is perhaps our most human response to the cosmic scale of violence. It is an acknowledgement of the danger and a declaration that we must seek to comprehend the forces that shaped us, so we turn the question to you. On this journey through the 25 most dangerous places, which cosmic danger fascinated or terrified you the most? Was it the rhythmic death ray of a pulsar, the silent eternity of the void, or the crushing pressure of a neutron star? Share your thoughts in the comments below. If you found this voyage into the mysteries of space compelling, be sure to subscribe for more journeys to the edges of